Welcome back, folks. I don't know if you realize this, but this is the last lesson for the semester. I originally had planned to go into chapter 12 a little bit, but it just feels a little unnecessary at this point. I feel like you probably got enough on your plate, and it's probably been tough enough to try to learn this on your own. Although I'm trying to teach, it's just, I don't know, it's so isolated. So we're not going to deal with the two sections of chapter 12 that I had on the calendar. They were extra information anyway, additional things that you will get to when you get to college algebra. So don't freak out that those were not required sections for our course. But these last two are, they're going to wrap up our quadratic unit, and then hopefully, again, you notice on the calendar that on Thursday, instead of a lesson, you're going to be taking another quiz. So you'll have your last lesson today, you got a quiz on Thursday. I'll probably leave that open for a couple of days just so you have enough time to get it done. And then that's it. Hopefully you've already taken a peek at the review for the final exam, and your final exam will be on Tuesday. Okay, so let's wrap up this last lesson. We're going to look at another set of applications for quadratics. Now, the first set of word problems we looked at were applications of quadratic equations. So we set up a quadratic equation and we solve to try to arrive at our answer. Here we're going to look at some applications of quadratic functions. So not one variable in our equation to solve for, but the relationship between two variables and something that we can represent on a graph. And then we're going to look at some quadratic inequalities. The inequality is not an equation or a function, but it will relate to both, okay? So what we're going to look at are what we call optimization problems. That means we're trying to maximize or minimize something in a situation. And if you are asked to find the maximum or minimum, and it could be a variation of one of the words, right? Instead of max or min, it could be highest or lowest or least or most or something like that. But if you're asked to find a max or a min or a highest or lowest value in a situation that contains a quadratic relationship, you have to be finding the vertex. The vertex. And that should make sense, right? If you have a quadratic relationship, your max or your min in the situation, whether it opens up or opens down, has to be at the vertex. Okay? So we're looking for a vertex. And remember our vertex, we used the letters H and K to symbolize where we were. And we said we could always find H using the formula, negative b over 2a, unless we were given the vertex form, right? Remember vertex form was your a and x minus h squared plus k. We could see our vertex at h and k, but if we were given standard form, which was the ax squared plus bx plus c, that there's no h and k directly shown in that form. So if we had vertex form, we can just pick out the vertex, great. If we have standard form, we're going to calculate the vertex using the formula. So h is negative b divided by 2a, and then we find k by taking h and plugging it in. Find k by plugging h in. Okay, so let's look at the first example. It says the value V in thousands of dollars of a certain stock after M months for a certain company, let's keep it really vague here, is given by V of M equals M squared minus 6M plus 13. What is the lowest value the stock is going to reach, and when will it reach that lowest value? So we have a parabola here, and since the leading coefficient is 1, I know the parabola opens up. So here's a parabola that represents the value. Think about this. I don't know where the parabola is. I'm just sketching out thought here. But the value over M amount of months. They want to know when is it going to be at the lowest. Again, that has to be happening at the vertex. So we need to find the vertex. And because this is in standard form, we're going to use our formula. So h, the first half of the vertex, we're going to find using negative b over 2a. So negative b, well, b is a negative 6. And then 2a, well, a is positive 1. That gives me a positive 6 over positive 2, which is 3. So that's the first half of the vertex. I'm going to find the other half by plugging that in. So now I'm going to take the 3, and I'm going to plug it in here, and I'm going to plug it in here. So k is going to equal 3 squared minus 6 times 3, and then plus 13. So, whoops, I meant to go to my calculator. Poor calculator's been busy. Okay, let's see. So we have 3 squared minus 6 times 3. Not that you couldn't do this you know, in your head, whatever, but I don't want to screw anything up. And then we're adding 13, and so we end up with 4. So 4 here. Okay, so that's the easy part. Plugging and chugging, using a formula, okay? No big deal. We did that last lesson. So right now we have a vertex at 3 and 4, but that vertex is out of context, right? If it was just a parabola with no context, we know that that is going to be the lowest point on that parabola, but we have to try to figure out what it means to this problem. So it's asking us what's the lowest value the stock is going to reach and when is it going to reach that lowest value. So it's 2 questions that are answered with the vertex, but which number answers which question, right? So think about what your vertex is. Now, we call it h and k just because that's what we call our vertex form, but if this is a point on the graph, this point would normally represent an x value in the point and a y value in the point, right? Well, if we go back to the function, we don't have x's and y's. In place of where we would normally have an x, we have an m. So instead of this representing some random x value, this represents an m value. And then for y, right, over here where we normally have a y equals, we have a v of m. So instead of this representing some random y value, this represents a value for v. So the maximum or the minimum value is 4, and that happens after 3 months. And actually it's 4,000 because it tells us here v is in thousands of dollars. So our interpretation of this vertex tells us the lowest, well, the lowest value is 3 that happens in, or 4 happens in 3 months. So let's make this concise here. In 3 months, it reaches a minimum value of $4,000. Okay, so that came from interpreting the vertex. That is the only hard part of this until we get to a later example, but let's keep it simple for a second. So next example, the profit P in dollars for a given company that produces G amount of goods is given by P of G equals negative G squared plus 980G minus 3,000. Find the maximum profit and the number of goods produced then. So this time the negative tells me that this parabola opens down, and that's why we're asked to find a maximum profit. So we're looking for the vertex, which is at the top of this parabola. Same formula though, h is going to equal negative b, so negative 980 over 2 times a, that's 2 times negative 1, and oh my gosh, I want my calculator, not the next screen. So a negative 980 divided by a negative 2, just so we don't screw this up, is a positive 490. And it's really easy to make sign mistakes on these, but think about when you're dealing with the contextual situation and actual problem. In most cases, negatives don't make any sense. If you were to get a negative, it wouldn't make sense to this problem. You're not going to have a negative amount of goods produced or negative dollars, okay? So positive 490 gets plugged in now. It's going to get plugged in for both of those g values, so k is going to equal a negative 490 squared plus 980 times 490, and then minus 3,000. And I don't know about you, but there's no way I'm doing that in my head. So we have a negative, and then a parenthesis, 490 squared plus 980 times 490. And then we're going to subtract 3,000, so 237,100. 237,100. So our vertex is at 490 and 237,100. Now again, it's just interpreting the vertex. Normally this would represent just a point with an x value and a y value, but there's context here. In place of x's, we have g's. So this is a value for g, and in place of where we normally have a y, we have p, so this is a p value. That means there was going to be a maximum profit of $237,100 produced with 490 goods. So when they produce 490 goods, they reach a maximum profit of $237,100. I don't know what they're producing, but that seems like a large profit for only making 500 of those things. Okay, all right, in any case, there it is. Now the next couple are going to be a little tougher, and hopefully you can recognize the difference. If we look at number 3, it says find the maximum product of two numbers that add to 24. A little difference in that we're not given a quadratic function, which means we're going to have to take an extra step to create a function before we can actually maximize it. So here, let's use the information, or try to translate the information they're giving us. It says to find the maximum product of two numbers that add to 24. So product has to be in here, and we're adding to 24, that's got to be in there somewhere, but we're looking for two different numbers. Now, normally when we're translating and solving an equation, we just want one variable, but remember, we're trying to write a function here, and the function has two variables. So we're looking for two numbers. We don't know what they are. What do you want to call the two numbers? I don't know. How about x and y? Okay, let's call my two numbers x and y. So one equation, let's write here for the product. Okay, the product, we don't know what the product is. Let's just call it p. The product of the two numbers, what would that look like if I multiplied my two numbers x and y? Oh, it would just be xy, right? And then it says that my two numbers add to 24. So let's write another equation for the sum. The sum of the two numbers is 24. That means if I added x and y, I get 24. Okay, you with me so far? I hope. So here we have two equations. Now neither one of them is quadratic, but we're going to have to use one to make the other quadratic. Now, how do we know what we want to make quadratic? We are trying to maximize the product here, which means our product equation is the one that needs to be a quadratic. So instead of an x times a y, what we need is an x times an x, or an x squared, or a y times a y to make a y squared. So got to get rid of one of those variables, and that's where the other equation comes in. In this second equation here, let's say I subtract x from both sides. What that tells me is that y is equal to a negative x in 24, or 24 minus x. Let's just say 24 minus x. Well, if I know that y is equal to 24 minus x, then I can replace y with what it's equal to. So if y is equal to 24 minus x, I am going to plug 24 minus x into the other equation for y. So now I'm looking at my product being, instead of x times y, it's x times 24 minus x. And if I distribute that out, that's 24x minus x squared. And let me just put that in order. That's a negative x squared and a positive 24x. Now I have my quadratic function. So now I gotta find the vertex of that quadratic function. And I have just taken all kinds of space here. So let me scooch some of this over. If only you could do that on your paper, right? All right, so now I need to find my vertex. So h is going to equal negative b, that's negative 24, over 2 times a, that's 2 times negative 1. So negative 24 over negative 2 is going to be positive 12. And then I'm going to find k by plugging that in. So a negative 12 squared plus 24 times 12 is, let's find out, negative 12 squared plus 24 times 12 is 144. So 144. Okay, so my vertex is 12 and 144. So normally, again, this represents an x value and a y value, but think about the function that we were looking at, the function that we just found the vertex of. Well, in place of x, oh, we still have x, so this still represents an x value, but in place of y, we don't have a y. What do we have? We have a p. So we know that p stood for product. There's a maximum product of 144, and one of the numbers is 12. That means the other number has to also be 12. But the only question here is find the maximum product. We did it right here, right? We have a max product of 144, and that's when x is 12. That's what it says in the vertex there, which means y has to also equal 12. Okay, now we're going to use a very similar process in the next one, so hopefully that made a little bit of sense. If not, hopefully it will come together here. So Gabby's fencing in a rectangular garden using the side of her house as one side of the rectangle. What's the maximum area she can enclose with 40 feet of fencing, and what dimensions yield that maximum area? So let's draw out what's happening here. She's going to be building or fencing in this rectangular garden, and her house is here. She says she's going to use one side of the house as one side of the rectangle. So what she's really fencing in is just these 3 sides, okay? And what's the maximum area? So we know we're going to be dealing with area here, that she can enclose with 40 feet of fencing. Now when she encloses this area, the enclosure, the actual fencing, is wrapping around the perimeter of the garden. So we need another equation there for perimeter, okay? So let's call, I don't know what the dimensions of this rectangle are, right? We're trying to find those dimensions. So let's call this x, and I know that this one would also be x, but this one here could be different, so let's call it y. The area that we don't know can be found by multiplying that length and width, that x and y. And the perimeter here it's 40 feet of fencing. So if I add up the 3 sides, the x, and the y, the 2 x's and the y, I get 40 feet of fencing. Okay? So this is the same situation we had. We are trying to find the maximum area. This function here, this equation here, has to be a quadratic, but it's got, instead of an x times an x or an x squared, it's got an x times a y. So let's get rid of the y. If I use my perimeter equation, subtract the 2x over, I can see that y is equal to 40 minus 2x. So if y is equal to 40 minus 2x, then I can replace y with 40 minus 2x. That means my new area function, my new area equation, becomes x times, instead of y, 40 minus 2x. So that is 40x, and then minus 2x squared, and then let me put that in order. So we have a negative 2x squared and a positive 40x. Now we can find our vertex, and again, I've just cut myself short on space. So let me move all this over as much as I can. Bear with me here, people. The last time you gotta bear with me, right? And then let me move this over. Okay, so now I'm gonna find the vertex. Let's see, h is gonna be negative b, so negative 40 over 2 times a, that's 2 times negative 2. Negative 40 over negative 4 is positive 10. Let's plug that in. Negative 2 times 10 squared, and then 40 times 10. Oh, that's sloppy over there. And let's see, 40 times 10 is, calculator, negative 2 times 10 squared plus 40 times 10 is 200. Okay, so we have a vertex at 10 and 200. And again, normally this would just represent some random x and some random y. But in the function that we found the vertex of, we do have x's, so this is still an x, but we don't have a y here. In place of y, we have a, which means our maximum area is 200. And let's see, from this, max area is 200 feet squared, and the dimensions, let's see, we know x is 10. What does y have to equal if x is 10? So let's go back and think about this for a second. If I know that this is 10 here and this is 10 here, what does the other dimension have to be to get to our area of 200 or to our perimeter of 40? Well, 20 or 200 divided by 10 means this would have to be 20. And then the 10, the 20, and the 10 would add up to the 40 for the perimeter, okay? So 10 is in the vertex, and then we determined that y has to equal 20. So move this, This tells me maximum area with a 10 by 20 foot enclosure. Probably no way you could fit all that on your paper, huh? X equals 10, y equals 20. Okay. All right, and that's about as tough as it can be until you get to college algebra. Those problems can be a little harder, but don't worry, I didn't give you a ton of those to work on your assignment. And if I put something on the quiz where you're maximizing, it's likely going to be like the first or second one. This is more just to, introduce you to a topic, okay? So don't freak out, and, feel free to watch it again if you need to. I know I went a little fast. All right, I'm just so excited. Okay, so quadratic expressions, equations, functions versus the last thing we have to cover is quadratic inequalities. Now, just so we're all clear, quadratic expression would look like this first box here. We don't have any equal sign and just one variable, and we know that, or if I gave you that quadratic expression, hopefully you would be factoring this, right? Factors of 4 that make 5. Factors of 4 that make 5 would be 1 and 4, and divided by 1 wouldn't change those, so the standard form for that expression would be what's given. The factored form would be x plus 1 and x plus 4, right? And that's really helpful, that factored form, not so much when we're looking at the expression, but when we're looking at the equation. If we put this equation, which now has an equal sign and one variable to solve for, if we put this equation in factored form, then we can see the solutions, right? We can see -1's a solution because it makes the whole thing equal 0, and we can also see that -4 is a solution because it makes the whole thing 0. I'm just using my scooch option a lot here, sorry. Okay, so the expression, we factor it, doesn't really do much for us, but in terms of an equation, it does. Now, how does that translate to the functions that we were looking at? Well, if I put this function, in factored form, okay, those solutions now, this solution of -1 and this solution of -4, those are only solutions if y is equal to 0. And if y is equal to 0, that means that's where this graph crosses the x-axis. So we have solutions here at x equals -1 and -4, and here, let me rewrite this, I'm sorry guys. So this x equals -1 and x equals -4 are the solutions. So we have solutions at x equals -1 and -4. But here, these solutions, again, only apply when y is equal to 0, which means they are the x-intercepts for the function. So we have x-intercepts, or roots. There we go, roots at -1, 0 and -4, 0. So just so you can see the connection between all these, right? If we're just looking at the expression, we could factor it, doesn't do much good. But the factored form of the equation shows us the solution, and the factored form of the function shows us where our graph crosses the x-axis. And again, the solutions to the equation are the roots for the function, okay? So the factors reveal the solutions, and the solutions of the equations are also the roots or x-intercepts of the function. I prefer the word roots, but just so I'm not losing anybody, roots are x-intercepts. Okay, so we can use a lot of words interchangeably. We can use the words solutions, roots, x-intercepts, and zeros. Would that one make sense? All interchangeably, because they're all the same, they have the same values, right? They all are showing us the same thing. So these are all interchangeable words. If I said to find the solutions to a quadratic equation, that is going to be the same thing as finding the roots to the function, and that would be the whole point of finding the factors in the expression, okay? And all of those are the solutions, roots, x-intercepts, they are what zero out those factors. All right, now how is this all gonna connect to a quadratic inequality? So solutions to quadratic equations, again, solutions to quadratic equations are the points where your related function crosses or touches the x-axis. Let's just say touches. Okay? If you're solving your equation, you get the exact points where your graph touches the x-axis. Now, solutions to quadratic inequalities are going to be the intervals, sorry, lost my word, are going to be the intervals where your related function are either above or below the x-axis. Now let me try to explain what's happening here, okay? So if I said to look at this quadratic function, and I said to solve that quadratic function, when I solve this, again, the factored form, the x plus 4 and x plus 1 equals 0, tells me my solutions are at -4 and at -1. And on the graph, that's where we see our parabola touch the x-axis, right? We see it touch at -4 and at -1. Now, that is, where is my function equal to 0? Where is it on the x-axis? If I change that equal sign to a less than sign, instead of asking where the function is equal to 0, I want to know where it's less than 0. So instead of where is the function on the x-axis, this less than is where is it less than the x-axis, where is it below the x-axis. And that is the piece of the parabola that I highlighted there that is below the x-axis. So from what x value to what x value, or over what interval, is that graph below the x-axis? The interval starts here and ends here. So we would say this graph is less than 0 from -4 to -1. Now notice the next one is also asking for less than, but it also has the equal to. That means it can be under and on the x-axis. So it's still going to go from -4 to -1. The difference is here we can equal the -4 and -1, so we'd put brackets. Then the one above we can't, so we would use parentheses. So this is below the x-axis. This is on the x-axis. This is below the x-axis. And this one is on and below. Both. Okay? Now notice here, in the next guy, it says where is this function greater than 0? Greater than 0. So on the x-axis is equal to 0. Less than is below, greater than is going to be above. Now this is the piece of graph that is above the x-axis, and this piece of graph is also above the x-axis. I just need to know what intervals correspond with those pieces. So this piece corresponds with all of these x's here, and the other piece is all the x's here. So we have two separate intervals for those two separate pieces. So this is, where is it above the x-axis? So the first interval goes from -infinity and it stops at -4. -infinity to -4. And the second interval starts at -1 and it goes to positive infinity. -1 to positive infinity. And because we don't have the equal to, we would keep all of this in parentheses, and we're just going to put a little union symbol in there. It's going to be those values or the others. And then this one, we're just going to be, same thing, it's above, but now we have the equal to. So the equal to tells us to use brackets. So everything from -infinity to -4, now including the -4, united with everything from -1 to infinity, and we include the -1. So this is on and above the x-axis. Okay? So, oh, this was supposed to be on the next page. I apologize for that. If we're going to solve a quadratic inequality, one way to do it would be to look at the best, I mean, not the best, this is my opinion. The most efficient way to do it is to look at the graph, but we don't have to make a whole fancy graph. We really just need to know where our graph hits the x-axis, because those points separate what's above and what's below. So if we're going to solve, we are going to find the roots to sketch. We're really going to do a rough sketch of the graph, or by using, you saw me use Desmos, or if you have a graphing calculator, your graphing calculator can do this for you too, and I'll show you both. Well, I'll show you the Desmos, but we can do this by hand without the calculator too. And then we're going to use the graph to determine our appropriate intervals. Are we looking above, below, what are we doing? So remember, greater than is above, or I don't think that's what I want to say here. Equal is on, greater than is above, and less than is below. Okay, those are the keys to this. So let's look at the number 5, this example here. If I wanted to solve this, I would treat it like an equation first. I'm going to factor. What are the factors of negative 30 that make negative 1? They would be negative 6 and positive 5, right? So if I factor this thing into x minus 6 and x plus 5, I know that it's going to be hitting the x-axis at 6 and at negative 5. Now, if I'm sketching this out, and really rough sketch, okay? Really rough sketch, I know at negative 5 it's going to hit the x-axis, and at positive 6 it's going to hit the x-axis. Now, I need to also know, if I'm making this rough sketch, which way the parabola opens. And because the first number here, a, is a positive 1, I know the parabola opens up. So it's going to open up, and it's going to go through these points. I don't know exactly what it looks like, but that is a good enough picture for me, okay? So now I can try to answer the question. The question was, where is this thing greater than 0? That is, where is it above the x-axis? That is this interval and this interval. Why my highlighter is so fat? So this interval corresponds with these x's, and this interval corresponds with these x's. So our solution is going to be the set of values going from negative infinity to negative 5, and no equal on the inequality means we're going to use a parenthesis here, and we are going to unite that with this interval, which starts at 6 and goes to positive infinity. That is our solution for this inequality. That is our solution set for this inequality. Let me using my tool again here. Okay. All right, let us try that again. So in this next one, we're gonna factor 2 times 2 is 4. Factors of 4 that make 5 would be 4 and 1. This time we have to divide them by 2, and that reduces. So this is going to factor into an x plus 2 and a 2x plus 1, which means my solutions, if this were an equation, would be negative 2 and negative 1/2. So if I went to sketch this out, and I don't care how accurate or equally proportioned these roots are, but at negative 1/2 and at negative 2, we're going to touch the x-axis. And again, because a is positive, right, because a is a positive 2, this opens up. So we're going to be opening up. Parabola's going to look something like that, okay? Could be wider, it could go farther. I don't really care. I just need to know where it is above or below. In this case, in particular, we're asked where is it below the x-axis, less than or equal to, is below or on. So this piece is below, and that starts here and stops here. So the solution set corresponds to the interval that starts at negative 2 and stops at a negative 1/2. And because this one has the equal to, we're going to include those endpoints with brackets. And that is our solution set for that inequality. All right, let's try that again. Now we got to be really careful here. Remember all of our factoring rules. This one, the first term is negative, so we're going to factor that negative out first. So a positive x squared, positive 15x, and a positive 56 greater than or equal to 0. So factors of 56 that make 15 would be 8 and 7. So we're looking at a negative x plus 7 and an x plus 8. So that means if this were just an equation, then it's going to be on the x-axis at negative 7 and negative 8. So rough sketch here. Again, I don't care that this is not equally spaced here, but negative 7, negative 8. And this time we have a negative out in front. So if a is negative 1, this thing is going to open down. So it's going to open down and go through those x-intercepts, something like this. Okay? So there's my picture. Now I need to know, where is this thing greater than or equal to, that is above or on the x-axis. This is the piece that is above the x-axis. That corresponds with this interval that starts at, this again, starts at -8 and ends at -7. So our solution set, again, starts at -8, ends at -7, and because this one has the equal to, we're going to include those endpoints with brackets. All right? I got one more for you to try. Feel free to pause the video and give it a shot. If not, just work along with me here. Again, we're going to factor out the negative, which gives me 3x squared plus 2x minus 5. And let's see, 3 times -5 would be -15. Factors that make 2 would be 5 and -3. Dividing by 3 and reducing, we see this factor into a negative, a 3x plus 5, and an x minus 1. So if this were an equation, the solutions would be at -5/3 and at +1. So -5/3 and +1, rough sketch, really rough. Okay, -5/3 is somewhere over here, +1 somewhere over here, and this negative, it tells me if a is -1 that this thing opens down. It's going to open down through those roots. So something like this, okay? And I covered up my 1. So now the question here was, where is this parabola less than 0? That is, where is it below the x-axis? This piece is below, this piece is below. And that corresponds with this interval and this interval of x's. So our solution set goes from -infinity to -5/3, and it gets united with 1 to infinity. And because we don't have the equal, all going to go in parentheses. Okay? Now I wanted to show you, I meant to earlier, but with Desmos, if you don't want to do a rough sketch and you're using the Desmos app, or you have a graphing calculator, you can use your calculator to make the sketch and then just read the graph the way we are, in this step right here. If you don't want to go through all the factoring and you have a graphing utility, you can use it. So if we just typed in -x squared, positive 15x, oops, -x squared, -15x, and -56, then we can see basically the same picture. Right, doesn't look exact because I didn't sketch it out to scale, but we see the parabola opening down and we can see where it touches the x-axis. So -8, -7, and we can see that little interval between -8 and -7 is where it is above. Okay, so if you want to use your graphing utility and skip the first couple of steps, you absolutely can. All right, a couple of special cases. X squared plus 4. X squared plus 4, what is happening with that graph? Well, that isn't factorable, is it? Okay, let's think about this as an equation for a second. X squared plus 4 equal to 0. If we were solving this, it doesn't factor, but we could subtract the 4 over and take the square root of both sides, and what we would see is we have imaginary solutions. Okay, imaginary solutions. This graph isn't going to touch the x-axis, and hopefully we can see this is technically our vertex form. This would be the same as having x plus 0 squared plus 4. So I could see my vertex is going to be at 0 and 4. What I have on this parabola is what I have going on in this graph is a parabola that has a vertex at 0, 1, 2, 3 here. And I know that it opens up. And so here's my picture. Okay, there's the picture. So from this picture, I'm asked, where is it above the x-axis? Well, this entire graph is above the x-axis, which means our solution set is everything. Everything from -infinity to +infinity. So all real numbers are solutions to the inequality. Now, if it was an equation, right, where would it be equal to 0? Nowhere. Not going to be on the x-axis anywhere, right? That's why we had imaginary solutions for that case. But if I want to know where it's above the x-axis, that happens to be everywhere, okay? Now, this is the same graph. Same graph, same picture, 1, 2, 3, 4. But this time, the question is, where is the graph below the x-axis? Where is it below? none of that graph is below the x-axis, which means this has no solution. Okay, so once in a while you'll get one of these special cases where your graph isn't above or below, or it's always above or below. So it's possible to have an infinite interval of solutions, and it's possible to have no solution set. Right? Otherwise, you're looking